All right, everyone, we are back and we are going to go through our exam 2 solution videos. We got it. All right, so sketch the time response to each system on the plot. What is the order of each system to determine if the system is stable, marginally stable? Okay, so we've got blue, we've got green, and we've got black. So let's go ahead and let's do first the order, and then we'll do like the stability here. So for the BLU. So for the blue, it's a second order system because we have two poles. For the green, it's a third order system. For the black, 1, 2, 3, it's a fourth order system. For the black, we are clearly unstable. For the blue, we are marginally stable. And for the green, we are indeed stable. Excellent. So let's go ahead and look at the time response. So if we have y of t, we know if I'm drawing the black curve, it's unstable, and maybe there's like some very high frequency like oscillatory motion here, but then it just explodes to positive infinity. So maybe there's some like high frequency, but then increasing. And it's high frequency, because of this values here are highest in terms of the imaginary axis. If we're looking at our dark blue function, it is going to have actually the lowest frequency, but it'll just be sinusoidal. So I'm just drawing for exaggeration. So, undo that. Sinusoidal in nature. And then finally, the green, it is going to have some basically exponential decay. So like the envelope here is actually quite sharp, but it may have some like increase here or decrease, and then it's just some oscillation or some decay here, something like that. Or if it decays here. So higher frequency than that. So if we're ranking, the frequency of oscillations, you could say that the blue will have, or the blue actually will have the lowest then green, medium, and then the black, at least if you consider it like this, it can be the highest, or you can say that this doesn't matter because it's exponentially increasing, and so the frequency of the oscillations for the green will be higher than that of the blue. So excellent. Look at the plots below, and plot the poles on the plots above. That's a fun statement. So this is just an exponential decay rate. So let's look at both of these. So this is an exponential decay. This has some frequency. This is clearly an unstable. So I'm going to call this 1, 2, 3. 3, I don't know what's happening, but I know maybe it looks like this. It's an exponential increase. So I should change color. So I'm just going to call this 3. And it has some oscillations, and it's increasing. This is an exponential decay. So 2 will have a real component. So 2 will have some real component here. And it's going to have some oscillations. So there can be a pole, and actually there can be a pole like this too. 2. So I can have some frequencies, and this is higher frequency. 1 is just an exponential decay, and now we can see, so it's only going to have a pole on the real axis, and it looks to decay faster than, or similar rate. So, but let's just kind of put 1 here. Whoops. Let's put 1. Whoops. I'm going to undo everything. Let's put 1 just on the real axis right here. There you go. So, did this. Look at the plots. Rank the frequency of oscillations. We've done that. Where's my red? Read the scenario below. Fill out the unit feedback system. Identify every component where the sensor and the actuator appear. Also write out the transfer function for the plant and write it out fully. So 3D printer uses a precision motion control, blah, blah, blah. Print is moving by the motor. The position of the print head is continually measured by an encoder, which converts mechanical rotation into electrical signal. In this system, there's electrical interference, and the encoder signal due to the printer's heat and motor drivers. So what do we have here? So we have our reference is what's the position we want our 3D printer. Our actuator is going to basically be here. So this is our actuator. Our sensor will be here, whatever our sensor basically looks like. So our sensor is actually that encoder, right? Our actuator is the motor, 3D printer. Control is the controller. So this is the position. So the controller gives a command output, and that command output is an electrical signal, right? That will basically influence like the voltage or control essentially if the motor is turning or not. So that's your electrical signal. That's going to be basically your command output from the controller. Controller is your microcontroller. E is your air. There doesn't seem to be any explicit disturbance in this system, but there is indeed noise. So if I'm looking at my plant function here is equal to the output, which is my y of s, over my input, which is my u of s. And my u of s is equal to, we can expand it out even a bit. So my u of s, my c of s is equal to my output u of s over my input, which is the e of s. And my e of s is equal to r of s minus my y of s plus my v, because there is some noise in this system. So you can rearrange those functions and write out your full plant. But that's it. So we'll see you next time.